Electromagnetic waves are similar to other waves, like water waves or sound waves, in that they carry energy from place to place. The energy in an electromagnetic wave is carried by both the electric and magnetic fields in the wave. In Chapter 19, we looked at the energy stored in a parallel plate capacitor, and more specifically, the electrical energy density stored in the electric field between its plates. The electric energy density is defined as the electric energy per unit volume, and we showed that it goes as the square of the electric field. Here, we have set the dielectric constant kappa equal to 1 since we are considering the electric field to be in vacuum or air. In Chapter 22, we looked at the energy stored in an inductor, which again can be considered as the energy stored in the magnetic field inside the inductor. In that case, the magnetic energy density, or energy per unit volume, is given by the following. Like the electric field case, the magnetic energy density goes as the square of the field. The total energy density of an electromagnetic wave is represented with a lowercase u, and it is just the sum of the electric and magnetic energy densities. We have seen how an electromagnetic wave self-propagates by utilizing a changing electric field, which creates a changing magnetic field by induction, and so on. Through this process, the energy density in an electromagnetic wave is shared equally between the electric field and magnetic field. Thus, the following must be true. We can write the total energy density in terms of just the electric field or just the magnetic field by making the appropriate substitutions in the total energy density. The fact that the energy densities in the two fields are the same allows us to set them equal to each other and discover a relationship between the electric and magnetic fields in an electromagnetic wave. What we find is that E and B are related simply by the speed of light. As an electromagnetic wave propagates, the electric and magnetic fields fluctuate sinusoidally in time. Therefore, the equations above give the energy density of the wave at a single instant in time for those particular values of E and B. However, we can calculate an average energy density of the wave, U average, by using average values for the electric and magnetic fields. In section 20.5, we faced a similar situation for alternating currents and voltages, which also varied sinusoidally. There, we introduced the RMS, or root mean square values for the current and voltage, and we can do the same thing here for the two fields. The RMS values of the electric and magnetic field are given by the following, where E0 and B0 are the maximum values of the electric and magnetic fields respectively. We can now use the relationships above to calculate the average energy density of the electromagnetic wave by using the RMS values for the fields. Electromagnetic waves transport energy from place to place, just like other waves do, and we can characterize this energy transport by using the intensity of the wave. When we studied sound waves in Chapter 16, we defined the intensity as the power that passes perpendicularly through a surface divided by the area of that surface. The intensity of an electromagnetic wave is defined in a similar fashion, where it is given by the electromagnetic power divided by the area of the surface. We can use this definition to relate the intensity to the total energy density. The intensity is given by the power per unit area, and the power can be written as the total energy divided by time. Thus, the intensity is equal to the total energy per unit time per area. Consider now the following figure, which shows an electromagnetic wave traveling in a vacuum along the x-axis. In a time t, the wave travels the distance c times t as it passes through the surface of area A. Consequently, the volume of the space through which the wave passes is c times t times A. The total, electric and magnetic, energy in this volume of space is given by the following. We can make this substitution into our expression for the intensity, which shows the intensity is simply related to the total energy density by the speed of light. We can substitute this result into the total energy density equations we derived earlier to obtain the following. This allows us to calculate the intensity of electromagnetic waves using both fields, or just E or B. Again, these relationships will calculate the intensity of an electromagnetic wave at some instant in time. If instead we use the RMS values for the fields, then we will calculate the average intensity.